Hey guys, so today I'm going to be going through Unit 5, Lesson 4 on gas laws. There are three main equations that you need to know. So grab a piece of paper, you're going to follow along and write this down with me. And these are the three equations you need to know for this: Boyle's law, Gay-Lussac's law, and Charles' law. So pause the video and write them down so that you can refer back to them and put them on like a separate part, because these are your like overall equations. And I'm going to add a couple things. For one, anytime you have temperature like T, you need to have it in units of Kelvin. If they give it to you in units of Celsius, to convert over to Kelvin, you can add 273 to get to Kelvin. And vice versa, if you have Kelvin and they want it in Celsius, which like they might ask for the final answer to be in Celsius, you can just subtract 273 to get it back to units of Celsius. Another thing to keep in mind is that temperature, we just said, is typically in units of Celsius or Kelvin, okay? Pressure, you will see that it is typically in units of atmospheres or kilopascals, or sometimes something called torr. So if you see these units, that is a pressure value. And then volume is typically in units of something cubed. Anything cubed is always going to be a volume. So like centimeters cubed, inches cubed. And then other units of volume include milliliters and liters for units of volume. So when you see that, you know that those are units for volume. So we're going to go back and basically we're going to go through the math problems from this lesson, and we'll refer back to these three equations. So let's look at this one first here. Ice Station Bravo near the North Pole launched a helium-filled balloon to check atmospheric conditions. At sea level, 1 ATM. Okay, I'm going to go ahead and write that down. 1.0 ATM. That is a pressure, because like I said, pressure is in units of atmospheres. At sea level, where the balloon was launched, it had a volume of 0.93. So the volume was 0.93 meters cubed. It rose to an altitude of 18,000. So like first it was down here and then it rose up to an altitude of 18,000. Like it went up really high in the sky, where up there the pressure dropped. And I forgot to write down what the pressure dropped to. This is problem number 8 though. So let me go look at that. The pressure dropped to 0.072. That's what it's supposed to say here. It didn't copy over. Atmospheres. Okay, so now the pressure is lower. It's 0.072 because we're higher up in the sky. What is the volume of the balloon at that altitude? So it's like my X. What's the volume at that altitude? Do you see how I'm writing it as I'm reading it? I'm kind of transferring it into like keywords. So first the pressure was at 1 atmosphere, and then it became to this atmosphere. So I'm going to call it P1 and P2. And you're going to have this in these problems. You're going to have like a before and an after. So it's going to be like P1 versus P2. This was my initial volume, and they want to know what it comes out to. Well, if we think about it, the pressure got lower, and so the volume is probably going to get bigger. And so we'll talk about that. So what equation should we use? It says, assuming that the temperature was the same. If you see something about something being the same or something being constant, it means that you can scratch it out and you don't have to solve for it or find it, because it's the same before and after. It's like a constant variable, and so you don't really have to worry about anything about it. So we don't have to look at that. So we need an equation that has P1 and V1 in it and P2 and V2, which is going to be Boyle's law right here. So let's go ahead and write that down. P1 V1 equals P2 V2. Now we're just going to plug in and solve. So 1.0 ATM is our P1, 0.93 meters cubed is our V1, my P2 is 0.072 ATM, and my V2 is X, okay? So I need to solve for X. So to do that, I need to get X by itself. Right now it's being multiplied by 0.072. So to undo a multiplication, I can divide by that so that it cancels out. And what I do to that side, I have to do to this side, 0.072 ATM. If you notice, my ATMs are going to cancel out because it's atmospheres divided by atmospheres. And now in my calculator, I just need to calculate my answer. It's going to be 1.0 times 0.93. Hold on. 1 times 0.93 divided by 0.072. And that is going to give me X. So I get that 12.92 equals X. And the units are going to be meters cubed because those are the only units that did not cancel out. So that's my X value. Your answer might be like 12.9. Just choose the one that's closest to that for your answer. Number 9, during an experiment, 575 mils. Okay, so what is that going to be? Is that going to be pressure or volume or temperature? It's going to be volume, right? Because volume measures units of milliliters. They are at 101 kPa. That's a pressure. kPa is always going to be a pressure. Okay, so kPa is pressure always. They were compressed to a new volume of 144. So this is like my new volume. It got smaller. They got compressed. What is the new pressure? What is my new pressure of the gas if the temperature remained constant? So this is, again, P1, V1. I'm sorry, that should say V1 right here. P1, V1 equals P2, V2. You're going to plug those in, and I'm going to have you try this one. Plug in and solve for X. You can pause if you need to write that down and then solve for X there. Let's look at the next one. A sample of 42 mils. Okay, that's a volume, right? My V1 is 42 mils. They were placed in a piston in order to maintain a constant pressure. Okay, so I could write down that my pressure is 101, but it says that it's constant. And anytime you see the word constant when you're dealing with these types of gas laws, you don't need to deal with it. It's going to be the same on both sides. If the gas were cooled from 20 degrees Celsius, that's a temperature. It started off at 20, and then it got cooled off, and its final temperature was negative 60 degrees C. What is its new volume? Okay, so it was cooled from 20 to negative 60, my T1 and T2. So what equation relates volume and temperature? Let's go back and see. Volume and temperature is going to be Charles's law. V1 over T1 equals V2 over T2. So we're going to write that down, and we're going to plug everything in, except my T has to be in units of Kelvin. So I'm going to add 273 to both sides to convert them to Kelvin. So you can do the math on that too. I'm getting 213 for this one, and then this one would be 293. That way we convert it to Kelvin because you're not supposed to use Celsius in these problems. So now we're going to plug everything in. My V1 is 42 mils, okay? My T1 is 293 K. My V2 is X, and my T2 is 213 K. Now I need to get X by itself. I can do that by, right now it's being divided by 213. So if I multiply both sides by 213K, it would cancel out, leaving me with X on that side, which is what I want. So I need to do it to this side too. And you can see that my K's are going to cancel out because they are exactly the same. And now I need to do 213 times 42 divided by 293. And when I do that, I get 30.5 mils as my answer because mils is the only unit left over. So this is going to be my answer for the new volume there. Okay, so for problem number 14, a tank of methane gas contains 2.8 meters cubed. Anything cubed is a volume. And it was at 20 degrees Celsius. So keep in mind, we need to convert that to Kelvin. So let's go ahead and do that, like add 273. So this is my Kelvin for it. The tank has a pressure release valve that releases gas into a secondary tank. So it has like one tank and it's 2.8 meters cubed, right? And then it has another like little tank and it can release and then flow into there. And that tank is 0.2 meters cubed. So my second volume is going to be 2.8 plus 0.2 because it's like adding on a second valve. So this is a situation where instead of saying the new total volume is 3, they're saying, well, we're adding on a little bit more. And they want you to think it through and think, oh, okay, I need to add those two together because there was a pressure release valve. So 3.0 meters cubed. at what temperature will the methane fill both tanks? So this is my X, and it says at what Celsius temperature. So we need to later convert it back to Celsius to get our answer. So we did an equation between V1, T1, V2, and T2, and that's going to be the V1 over T1 equals V2 over T2. So let's go ahead and plug in. So 2.8 over 293 equals, what's my V2? My V2 is 3.0 divided by, and I'll do this in red, my X. My X is on bottom, okay? When your X is on bottom and you've got two fractions like this, you basically need to get X back on top. One quick way to do that would be to cross multiply. So when you have a fraction on a double fraction on both sides and X is on the bottom, then cross multiply, which means that you can rewrite it so that it's like 2.8 times X equals 3.0 times 293. So we need to do 3 times 293 for this right here. So I'm getting that 2.8 times X equals 879. And now we can divide both sides by 2.8 to get that to go away. Divide by 2.8. And this is my temperature. But remember that that's in units of Kelvin because we have to have it in Kelvin. And it says at what Celsius temperature. So let's subtract 273 from that to get it back to units of Celsius. And I'm getting 40.9, which can round maybe to 41 degrees Celsius as my answer there. All right. Next one, the tire pressure in an automobile tire. Okay, so the pressure was 2.38. I'm going to write that down. When the tire was at 26 degrees C. Okay, so my temperature is 26. I'm going to go ahead and add 273 because I know that I need to do that. So that is 299 Kelvin. As the automobile drove for several hours, the temperature of the tire increased to 93 degrees C. So let's add 273 to that. And I'm getting 366 for my new Kelvin there. And it says, what is the new tire pressure? So that's like my X, right? So I have a P1, a T1, a P2, and a T2. So looking at my equations here, I'm going to use Gay-Lussac's law. P1 over T1 equals P2 over T2. And just plug everything in. Okay, so 2.38 divided by 2, it's a point right there, 299 equals X divided by 366. I need that 366 to get away from my X because my X is in the numerator where it's supposed to be already. We just need that to go away to get X by itself. So I need to multiply both sides by 366. And now we just do the math. So it's 366 times 2.38 divided by 299. So whenever I multiply all those together, I get that X equals 2.91, and my unit will be atmospheres because it will match the other unit of pressure there. So 2.91 is my answer. All right, last one. This 3.25, I already know that's going to be a volume. It has 3.25 liters of gas. The temperature is negative 150. So let's go ahead and add 273 to that because I know that I need to. So 273 minus 150, I'm getting 123K. Okay, and it has a pressure of 506 kPa. Okay. When the canister was allowed to warm up, the gas inside reached a new pressure of 1214. It reached a new pressure. So that's my P2 versus my P1. What was the Celsius temperature of the gas? The volume remained constant. So my volume stayed at 3.25. So remember that when it's constant, we don't have to worry about it. And so we just are dealing with P1 and T1. And then P2 and T2. So this is the equation we're going to use here, right? And so we're going to plug everything in now and solve for the new Celsius temperature. So my P1 is 506 divided by 123 Kelvin. And that is equal to my P2 is 1214 divided by my X. So my X is on the denominator. That's not good. So I'm going to cross multiply to find X. And I'm going to have you guys try to solve for it from here. So cross multiply to solve for X. And you need to write it down because after you cross multiply, you got to solve for X. And then it wants it in degrees Celsius. And it's going to come out in degrees Kelvin. So remember that after you solve for X, subtract out 273. This is the exact same as the one that we did right here where I cross multiplied and then I subtracted out 273. So rewind if you need to and look at problem number 14. And it's going to be the same formatting except just literally different numbers. So if you feel overwhelmed, go back and rewatch problem 14 and challenge yourself and say, okay, I'm going to try one more time and then solve for X. And then if you have any questions at all, please let me know. Come with your piece of paper to my classroom and I'm happy to help you. Have a great day.